I left Los Alamos in October of 1945, not long after the war ended, and for a long time afterward I told myself the worst of it was behind us, that whatever came next for that laboratory, it would be politics, not danger, that occupied the people who stayed. I was wrong about that, and I've spent a long time thinking about why I was wrong, because the mistake that nearly cost more lives after the war than during it wasn't a mistake in judgment or in courage. It was a mistake in something far more mundane and far more dangerous. Familiarity. To understand what happened, you have to understand a piece of hardware that existed at Los Alamos, one that the men working with it had given a nickname long before anyone thought the name might turn out to be literal. They called it the Demon Core. It was a sphere of plutonium roughly the size of a grapefruit, weighing just over 6 kilograms, manufactured in the summer of 1945. It had been built as the third plutonium core produced by the project. The first had been used in the Trinity test that July, the second in the weapon dropped on Nagasaki in August. This third core had been completed too late to be used in the war. Japan surrendered before it was ever needed, and so the sphere sat at Los Alamos afterward, not as a weapon anymore, but as an object of continued scientific study, because the physicists there still needed to understand with real precision how close a mass of plutonium like this one could be brought to criticality, and by how much, before it became genuinely and irreversibly dangerous. I want to explain the physics of what they were actually doing, because the experiment itself wasn't reckless in its conception. It had a name, criticality testing, and it served a real purpose. A sphere of plutonium sitting alone in open air is subcritical. Neutrons produced by the small amount of natural fission occurring inside it mostly escape from the surface before they can strike another nucleus and continue a chain reaction. But if you surround that same sphere with a material that reflects neutrons back inward, bounces them back into the plutonium instead of letting them escape into the surrounding room, you can push the same mass of material closer and closer to criticality without adding a single additional gram of plutonium. The neutron reflector does the work that additional mass would otherwise have to do. Beryllium is an extremely effective neutron reflector, and the technique developed at Los Alamos for studying this used 2 hemispherical shells of beryllium, which technicians would carefully bring together around the plutonium core, closing the gap between them by small, controlled amounts, watching neutron counters the entire time to measure how the radiation level climbed as the reflector closed in. The idea was to approach the edge of criticality closely enough to gather real, precise data about the core's behavior while stopping well short of the point where the assembly would actually go critical and the chain reaction would become self-sustaining. It was called, with a certain grim humor that scientists sometimes develop around genuinely dangerous work, tickling the dragon's tail. You were meant to get close enough to feel it stir and pull back before it woke. The first fatal accident happened on the 21st of August, 1945, barely 2 weeks after the war had ended, while I was still winding down my own responsibilities at the laboratory before my departure. A physicist named Harry Daghlian was working alone that night, which was already, in hindsight, a departure from how this kind of experiment should have been conducted. He was using a slightly different configuration than the beryllium hemispheres, stacking neutron-reflecting tungsten carbide bricks around the same plutonium core, one at a time, watching the neutron counters as he went, checking how close he could bring the assembly to criticality using this particular reflecting material. Late in the evening, while placing what he intended to be the final brick, he realized partway through the motion that the neutron counters were showing the assembly was about to go supercritical, that this last brick would push it over the edge into an actual self-sustaining chain reaction. He tried to withdraw his hand and pull the brick back. He fumbled, and the brick slipped from his fingers, falling directly onto the assembly. For a fraction of a second, the mass went supercritical. The room filled with a blue glow, Cherenkov radiation, the same phenomenon you see in the water surrounding certain types of nuclear reactors, produced when charged particles move through a medium faster than light travels through that same medium. Daghlian felt a distinct heat wash across his skin, and he understood immediately, with the particular clarity that comes from having spent years studying exactly this kind of physics, what had just happened to him. He didn't panic. He worked quickly and deliberately to disassemble the pile, removing the brick, pulling the components apart to stop the reaction, even though every second he spent doing so meant additional exposure. He then triggered the building's alarm and sought help. He had absorbed a massive dose of radiation in that instant, later estimated at around 510 rem, a level of exposure that no medical treatment available at the time, or arguably any treatment available today, could fully counteract. He died 25 days later, on the 15th of September, from acute radiation sickness, having spent those final weeks watching his own body fail in ways the doctors treating him had only ever read about in theoretical terms. I want to sit with something here because I think it's the part of the story that matters most to understanding what came next. The laboratory investigated the accident. They understood with real precision exactly what had gone wrong physically. The specific configuration of tungsten carbide bricks, the exact neutron multiplication that had occurred, the dose Daghlian had received, and the most important lesson that should have come out of that investigation was procedural, not just physical. Never conduct this kind of experiment alone. Always have a second person present, both as a safety check and, if something goes wrong, as someone capable of responding immediately. That lesson was written down. It was understood, at least on paper, by the people running the laboratory. And less than 9 months later, it failed to prevent almost the exact same accident from happening again to a different physicist using the very same plutonium core. Louis Slotin was, by every account I've ever heard from people who knew him, one of the most talented experimentalists at Los Alamos, a Canadian-born physicist who had played a direct, hands-on role in the final assembly of the Trinity device itself, someone whose comfort and skill working with fissile material under dangerous conditions was, by 1946, almost unmatched at the laboratory. That skill, I think, is part of what makes this story so difficult to sit with, because it wasn't inexperience that killed him. It was a kind of practiced confidence that had, over dozens of repetitions, worn down the margin of caution that the work actually demanded. By May of 1946, the Demon Core was being used again, this time with the beryllium hemisphere configuration rather than tungsten carbide bricks. And Slotin had developed a technique for this experiment that horrified some of the physicists who watched him perform it, even at the time, well before anything went wrong. Instead of using the mechanical shims and precise spacers that were meant to control the gap between the two beryllium hemispheres as they were brought together, Slotin would hold the upper hemisphere balanced on the blade of a standard flathead screwdriver, using the screwdriver itself as the spacer, controlling the gap by hand, adjusting the angle and pressure with his own fingers while the neutron counters clicked away beside him. This was by the safety standards the laboratory itself had supposedly adopted after Daghlian's death, an extraordinarily dangerous way to conduct the experiment. There was no mechanical safeguard preventing the screwdriver from slipping. There was nothing physically stopping the upper hemisphere from dropping fully onto the lower one if Slotin's hand faltered even for an instant. And yet he had performed this exact procedure, this exact way, dozens of times before, successfully without incident. Enough times that people who watched him, including some who found the method deeply unsettling, had also come to see it as something he had, in some sense, mastered. On the 21st of May, 1946, Slotin was conducting what would be his final experiment with the demon core, demonstrating the procedure for a small group of colleagues gathered in the room, several of whom were standing close enough to watch directly, as he lowered the upper beryllium hemisphere toward the lower one. Balanced on the screwdriver blade as always, the screwdriver slipped. The upper hemisphere fell fully onto the lower one. For an instant, the assembly went supercritical, far more severely than what had happened to Daghlian, because this time there was no gradual approach, no last brick placed carefully. It was a sudden, complete closure of the reflector shell around the plutonium core, an uncontrolled excursion that released, in that fraction of a second, a burst of radiation and heat intense enough that people in the room reported feeling it directly, a wave of warmth across their skin, and seeing the same blue glow of Cherenkov radiation that had filled the room during Daghlian's accident 9 months earlier. Slotin's reaction in that instant was almost certainly the reason everyone else in the room survived, rather than trying to carefully disassemble the apparatus using proper procedure, which would have taken precious seconds, during which the reaction, still critical, would have continued to release radiation. He used his bare hand to physically knock the upper hemisphere off the assembly, flinging it to the floor, immediately stopping the chain reaction. It was an instinctive, almost violent act, and it very likely saved the lives of everyone else standing near him that day. But in doing it, his own hand and body absorbed a dose of radiation even more severe than what Daghlian had received, estimated afterward at somewhere near 1,000 rem, a level that left essentially no realistic chance of survival, even with the best medical care available anywhere in the world at the time. He died 9 days later, on the 30th of May, 1946. The physicians who treated him documented in painful clinical detail the progressive failure of his body over those 9 days, the kind of deterioration that radiation sickness produces at that dose level, a process that medicine could observe and record but not meaningfully slow. 2 men, using the same plutonium core, killed by nearly identical accidents, less than a year apart. I've thought about why this happened twice, at the same laboratory, among people who understood the physics involved better than almost anyone alive at the time, and I don't think the answer is a comfortable one. It wasn't ignorance. Every person in that room in May of 1946 understood with real precision what a supercritical excursion would do to a human body. The danger wasn't abstract to any of them, and yet the practice of using a screwdriver as an improvised spacer had become normalized in that specific laboratory culture in a way that let real, quantifiable risks slide slowly out of people's immediate attention simply because it had worked safely so many times before. There's a particular kind of physics mistake that isn't really about the mathematics at all. The mathematics of criticality was by 1946 extremely well understood by the people doing this work, arguably better understood than almost any other area of experimental physics at the time, given how much of the war effort had been devoted to exactly these calculations. The mistake wasn't in the equations, it was in the gap between what the equations demanded in terms of procedural discipline and what human beings working under time pressure, growing comfortable with genuinely lethal material through sheer repetition, actually did with their hands in the room. After Slotin's death, the laboratory ended hands-on criticality experiments of this kind entirely. Remote-controlled mechanisms operated from a safe distance replaced the practice of physicists standing directly over an assembly, manually adjusting the distance between fissile material and its reflector. The demon core itself, the very sphere of plutonium involved in both deaths, was eventually melted down and its material repurposed. Its specific identity as an object folded back into the broader supply of plutonium the laboratory continued to work with, though the name people had given it, born originally as gallows humor among physicists who thought they understood exactly how dangerous their own equipment could be, stayed attached to the story in every account written afterward. I've turned this story over many times since I first heard the details, because I think it says something uncomfortable about the whole endeavor I'd spent years leading. We had built, at Los Alamos, one of the most disciplined, rigorously checked scientific enterprises in human history. Every calculation cross-checked, every design decision reviewed by multiple independent groups, every uncertainty quantified as precisely as the physics of the time allowed. And within that same culture of rigor, a practice as casually dangerous as balancing a beryllium hemisphere on a screwdriver blade had become, for one particular physicist, simply routine. Familiarity is not the same thing as safety, no matter how much it can feel that way from the inside. The equations don't care how many times you've gotten away with something before. They only describe what happens the moment you don't. I think about Daghlian and Slotin both. Whenever I hear people talk about the physics of nuclear weapons purely in terms of yield calculations and critical mass geometries, as though the danger of this work began and ended with the weapons themselves. It didn't. The same core that had never been detonated as a weapon, that sat quietly at Los Alamos after the war as an object of pure scientific study, killed two brilliant, careful men through nothing more dramatic than a slipped screwdriver and a habit that had, slowly and invisibly, stopped feeling as dangerous as it actually was. That, I've come to believe, is the real physics mistake in this story. Not an error in a calculation, but an error in how easily human beings can let genuine danger become ordinary, simply by living alongside it long enough. The plutonium never changed. The physics of criticality never changed. What changed, quietly over dozens of repetitions, was how carefully the people standing closest to it were paying attention. And by the time anyone paid attention again, it was already too late to matter.